In 2004, a massive aerospace assembly facility in Shenyang, China, was operating under a strict licensing contract to build 200 Russian Sukhoi Su-27 air superiority fighters. 95 units into the production run, the Chinese government abruptly halted the assembly line. They packed up the tooling, voided the multi-billion-dollar contract, and informed Moscow that the aircraft simply no longer met their operational requirements. It was a severe geopolitical slight, leaving Russian aerospace executives furious and financially stranded. Yet a suspiciously short time later, an aircraft rolled out of those very same Shenyang hangars that was visually indistinguishable from the Su-27. It possessed the same sweeping, unmistakable swan-like silhouette. It cast the identical radar signature. It housed the same massive internal fuel volume. But beneath the aluminum and titanium skin, the internal architecture was entirely alien to the original designers in Moscow. The Chinese had not just copied the jet, they had gutted its nervous system and replaced it with their own. This is the central paradox of the Shenyang J-11B. It is an aircraft that looks like the pinnacle of late Cold War Soviet engineering on the outside, yet functions as the foundational testbed for 21st century Chinese aerospace dominance on the inside. To pull this off, Chinese engineers had to achieve something arguably more difficult than designing a fighter from scratch. They had to flawlessly map, decode, and reverse engineer one of the most aerodynamically complex, naturally unstable airframes in aviation history, all without access to the original Russian source code, aerodynamic stress data, or fly-by-wire control laws. They took a closed-system analog masterpiece and forcefully wedged an entirely different digital technological ecosystem inside it. The story of how this happened requires looking back at the desperate state of the People's Liberation Army Air Force in the early 1990s. At that time, the bulk of their fleet consisted of J-7s and J-8s, heavily modified derivatives of the archaic Soviet MiG-21. These were fast interceptors, but they lacked range, advanced radar, and the dogfighting maneuverability required to contest modern airspace. Across the ocean, Western powers were fielding advanced F-15 Eagles and F-16 Falcons. The Chinese were hopelessly outclassed. The collapse of the Soviet Union provided a miraculous, albeit chaotic, shopping opportunity. A cash-strapped Russia was suddenly willing to export its crown jewels to keep its defense industry from starving. China seized the opportunity, purchasing an initial batch of fully built Su-27 SK fighters. These aircraft were heavy, twin-engine, long-range air superiority fighters designed specifically to hunt American F-15s over the vast stretches of Europe and the Arctic. If you enjoy detailed deep dives into military engineering and strategy, subscribe to the channel. I've got a lot more planned. The initial purchase quickly evolved into Project 906, an agreement where Russia would supply kits and components for China to assemble the aircraft domestically under the designation J-11A. For a few years, everything proceeded according to the contract. The Shenyang Aircraft Corporation painstakingly assembled the Russian parts. But assembly is not the same as understanding. The Chinese military leadership realized that as long as they relied on Russian radar, Russian avionics, and Russian engines, they would remain tethered to Moscow's political whims and technological limitations. The Russian analog gauges were outdated, the avionics were notoriously heavy, and the weapons suite restricted China to buying Russian missiles. To break this dependency, Shenyang initiated a shadow program. They intended to take the physical geometry of the Su-27 and silently swap out every internal system for indigenous technology. But cloning the shell was only half the battle. To understand the sheer technical audacity of the J-11B program, you have to look at the geometry of the theft. The Su-27 airframe is a marvel of integrated aerodynamic design. Developed by the Soviet Central Aerohydrodynamic Institute, the aircraft features a blended wing-body layout. The fuselage actually generates a significant portion of the aircraft's lift, rather than relying solely on the wings. Furthermore, the engines are spaced widely apart, creating a large tunnel beneath the fuselage that helps manage airflow at high angles of attack while providing massive internal volume for fuel. Crucially, the airframe is designed with relaxed static stability. In simple terms, the aircraft naturally wants to flip out of control. It is aerodynamically unstable, which makes it incredibly agile, but it requires a sophisticated fly-by-wire computer system to make micro-adjustments to the control surfaces hundreds of times a second just to keep it flying straight. When the engineers at Shenyang decided to strip out the Russian internals and replace them with Chinese systems, they triggered a cascading series of engineering nightmares. In aircraft design, every component's weight and physical placement is meticulously balanced to maintain the exact center of gravity. If you change a component, you change the weight. If you change the weight, you shift the center of gravity. If you shift the center of gravity on an aerodynamically unstable airframe, the original fly-by-wire computer laws become useless. The jet will simply tear itself apart in the air. This brings us to the first massive hurdle, the radar. The original Su-27 used the Soviet N-001 radar system. It was a formidable piece of equipment for its era, but it was incredibly heavy, relying on a massive, physically rotating Cassegrain antenna. The entire assembly weighed close to 1,000 pounds. Chinese engineers wanted to replace this with a domestic planar array radar, the Type 1493, which was significantly lighter, possessed better target discrimination, and could track multiple targets more efficiently. But there was a steep price to be paid for this modernization. By removing the heavy Soviet radar from the nose and installing the lighter Chinese radar, the engineers inadvertently shifted the aircraft's center of gravity backward. An aft center of gravity on a relaxed stability airframe is catastrophic. It induces a violent pitch-up tendency that the Russian flight computers were not programmed to counteract. Because China did not have the Russian source code for the fly-by-wire system, they could not simply type in a new variable for the radar weight. They had to completely rewrite the flight control laws from scratch, relying on painstaking wind tunnel testing and dangerous live test flights to map out the aerodynamic boundaries of their newly balanced jet. To solve the center of gravity issue without adding useless dead weight to the nose, the engineers had to radically alter the airframe's material composition. The original Soviet airframe relied heavily on conventional aerospace alloys, aluminum and steel, with titanium used in high-stress areas. The Shenyang team began substituting these metals with advanced carbon fiber composites, particularly in the vertical stabilizers, the tail sting, and the wing roots. By removing weight from the rear of the aircraft, they managed to pull the center of gravity forward again, balancing the lighter radar in the nose. This composite integration also had the side effect of slightly reducing the aircraft's overall weight, which theoretically improved its thrust-to-weight ratio. However, solving the airframe physics immediately exposed an even more daunting challenge: propulsion. The heart of the original Su-27 and the licensed J-11A was the Russian Saturn AL-31F turbofan engine. This engine was a masterpiece of Soviet engineering, providing massive thrust, excellent high-altitude performance, and the raw power necessary to push a heavy fighter through the sound barrier while pulling 9 times the force of gravity. The Chinese military knew that true aerospace independence was impossible without mastering jet engine technology. Therefore, the indigenous J-11B was slated to be powered by a completely domestic engine, the Shenyang WS-10 Taihang. Developing the WS-10 proved to be a multi-decade saga of frustration, failure, and intense industrial espionage. Reverse engineering a static structural component like a wing spar is a matter of metallurgical analysis and machining. Reverse engineering a high-performance military turbofan is an exercise in managing extreme thermodynamics and centrifugal forces. Inside the combustion chamber and high-pressure turbine of a jet engine, temperatures exceed the melting point of the metal blades themselves. To prevent the engine from melting, engineers must manufacture turbine blades out of single crystal superalloys cast with intricate internal cooling channels that allow cold bleed air to form a protective boundary layer over the metal. When the Chinese first attempted to build the WS-10, their metallurgy simply wasn't up to the task. Early iterations of the engine suffered from horrific quality control issues. The turbine blades would experience metal creep, stretching and deforming under the immense heat and rotational stress, eventually grinding against the engine casing or shattering entirely. Furthermore, the electronic engine controls were sluggish. When a pilot slammed the throttle forward, there was a terrifying delay before the engine spooled up and delivered thrust. In a dogfight, a 2-second delay in thrust response is the difference between evading a missile and being utterly neutralized. The integration of the WS-10 into the J-11B airframe forced a brutal compromise. Because the domestic engines were so unreliable in their early iterations, the People's Liberation Army Air Force found themselves with a fleet of brand-new, domestically produced fighters that pilots were hesitant to push to their limits. Maintainers were working grueling hours, swapping out WS-10 engines at an alarming rate just to keep a handful of aircraft on the flight line. The factory life of an early WS-10 was a fraction of the already notoriously short lifespan of the Russian AL-31F. This operational friction rippled through the squadrons. Pilots transitioning from the older J-11As, powered by the trusted Russian engines, were highly skeptical of the new J-11Bs. If you were flying a long-range patrol mission over the vast, unforgiving expanses of the South China Sea, the last thing you wanted was a domestic experimental engine coughing and losing thrust hundreds of miles from the nearest runway. For years, the Chinese military quietly continued purchasing Russian AL-31F engines specifically to equip certain batches of the J-11B, simply because the operational readiness rates of the domestic WS-10 were unacceptable. It was an embarrassing reality for an aerospace sector desperate to prove its independence, a stark reminder that physics and metallurgy cannot be rushed by political mandates. The operational reality of the early J-11B forced the Chinese Air Force to adapt their tactics around the machine's limitations. While the airframe retained the legendary agility of the flanker family, the sluggish engine response meant that pilots had to fly with aggressive anticipation. They could not rely on brute force acceleration to escape a low-energy state. Instead, they had to manage their kinetic energy with extreme precision, avoiding the high angle of attack maneuvers that the aircraft was technically famous for, simply because bleeding off speed was too risky if the engines took too long to push them back to a safe velocity. Yet, as grueling as the propulsion issues were, the J-11B's avionics and weapons integration told a different story. Here, the Chinese leapfrogged their Russian mentors. The cockpit of the original Su-27 was an ergonomic nightmare, a sea of analog dials, steam gauges, and mechanical switches that placed a massive cognitive load on the pilot. Navigating, operating the radar, managing electronic warfare systems, and actually flying the aircraft demanded constant heads-down attention. The Shenyang engineers completely modernized this workspace. They installed a wide-angle holographic head-up display and multiple large-color multifunction displays. The glass cockpit of the J-11B allowed pilots to absorb tactical data at a glance, drastically improving situational awareness. This digital overhaul was not just for pilot comfort, it was mandatory for the integration of domestic weaponry. The Chinese wanted to break free from relying on the Russian R-27 and R-73 air-to-air missiles. They possessed their own indigenous weapons, specifically the PL-8 short-range infrared missile and the PL-12 active radar homing beyond visual range missile. But integrating these weapons presented another bizarre physical challenge. The PL-8 missile is physically larger and significantly heavier than the Russian R-73. More problematically, it features unusually wide aft stabilization fins. When ground crews first attempted to mount the PL-8 onto the standard wingtip rails of the J-11B, they discovered that the wide fins of the missile would physically strike the wing structure. The missile simply didn't fit. To solve this, Shenyang engineers had to design a highly specific, uniquely stepped pylon for the outer wing stations. This offset pylon lowered the missile and angled it outward, providing enough clearance for the fins. But again, resolving one engineering problem immediately introduced an operational penalty. The bulky stepped pylons disrupted the smooth airflow over the wingtips, adding a noticeable amount of parasitic drag to the airframe. This drag marginally reduced the aircraft's top speed and acceleration, forcing yet another compromise on the already struggling WS-10 engines. It was a classic example of the cascading consequences of reverse engineering. Modifying an airframe to carry a weapon it was never intended to carry required aerodynamic sacrifices that penalized the overall performance of the platform. So, after looking at the sheer difficulty of rewriting a jet's DNA from scratch, rewriting control laws, suffering through engine metallurgy failures, and modifying pylons just to make missiles fit. Do you think China's strategy of copying and pasting an airframe was worth the massive reverse engineering headaches? Let me know in the comments. Despite the drag penalties and the early engine woes, the integration of the PL-12 missile transformed the J-11B into a genuine beyond visual range threat. Unlike the older Russian R-27, which required the launching aircraft to keep its nose pointed at the target to guide the weapon all the way to impact, the PL-12 possessed its own active radar seeker. A J-11B pilot could track a target on the new domestic planar array radar, launch the PL-12, provide initial mid-course guidance updates, and then defensively turn away. Once the missile got close enough to the target, its internal radar would activate, autonomously hunting down the enemy. This fire-and-forget capability finally brought the Chinese Air Force into parity with Western fighters carrying the AIM-120 AMRAAM. When you compare the fully mature J-11B to its primary regional rival, the American F-15C Eagle, a fascinating contrast in design philosophy emerges. The F-15 is essentially a flying manifestation of brute force. It relies on massive, highly reliable engines and a large, rigid wing to dominate the high-altitude, high-speed energy fight. It was designed to climb fast, shoot fast, and maintain a high-energy state. The J-11B, retaining the flanker's aerodynamic DNA, is a different beast entirely. It excels in the slow-speed, high-angle of attack regime. If a dogfight degrades into a turning engagement at lower speeds, the J-11B's blended wing body and relaxed stability allow it to point its nose at angles the F-15 simply cannot achieve without stalling. However, modern air combat rarely devolves into close-range turning fights. It is largely a sensor and electronic warfare battle conducted at ranges exceeding 50 miles. Here, the F-15C, especially those upgraded with AESA radars, held a distinct advantage over the early J-11Bs. The Chinese planar array radar was a massive leap over the Russian analog systems, but it was still fundamentally mechanically steered technology. It took time to scan a volume of airspace, and it was susceptible to advanced electronic jamming. The pilots flying the J-11B understood this reality. Operational doctrine shifted to capitalize on the aircraft's massive fuel capacity. Unlike the F-15 or F-16, which often require external drop tanks that add drag and limit maneuverability, the J-11B carries a staggering amount of fuel internally. This allowed Chinese squadrons to project power far out into the East China Sea and the Taiwan Strait without relying heavily on vulnerable aerial refueling tankers. They could loiter on combat air patrol for hours, operating as long-range interceptors designed to push hostile sensor platforms and fighters away from the Chinese coastline. Over the years, the relentless pace of Chinese industrial investment began to grind the J-11B's early problems into submission. The persistent metallurgical issues plaguing the WS-10 Taihang engine were slowly diagnosed and rectified. Advances in materials science led to better single-crystal turbine blades, and refined manufacturing tolerances significantly improved the engine's reliability and thrust output. By the mid-2010s, newer production batches of the J-11B were finally flying with WS-10 engines that maintainers could actually trust. The agonizing delays in throttle response were programmed out via upgraded digital engine control software. The aircraft finally began to achieve the kinetic performance that its aerodynamic shape had always promised. The modernization of the J-11 fleet did not stop with fixing the engines. As the airframes accumulated flight hours and underwent depot-level maintenance, many were subjected to extensive midlife upgrades. The most significant of these was the transition to the J-11BG standard. This upgrade completely stripped out the older Type 1493 mechanical radar and replaced it with an advanced domestic AESA radar, recognizable by a lighter-colored nose radome. This radar swap was another massive technological leap, mirroring the ongoing evolution of Western fighters. An AESA radar does not physically move. Instead, it steers its radar beams electronically via thousands of small transmit-receive modules. This allows the J-11BG to scan airspace almost instantaneously, track dozens of targets simultaneously, and operate with a much lower probability of being intercepted by enemy warning receivers. With this upgrade, the J-11 airframe transitioned from a 1980s aerodynamic marvel struggling with 1990s avionics into a highly capable 4.5 generation fighter, heavily armed with the latest PL-15 long-range missiles. But the true legacy of the J-11B is not found purely in its combat specifications. Its most profound impact lies in its role as a massive flying classroom for the Chinese aerospace industry. The painful multi-decade process of reverse engineering the Su-27, failing to build engines, crashing against metallurgical limits, writing new flight control laws, and ultimately succeeding, forced the entire Chinese defense sector to mature. They didn't just learn how to copy an aircraft, they learned how aircraft fundamentally work at a systemic level. If they had simply continued purchasing Russian fighters, they would have remained heavily dependent clients. By stealing the blueprint and forcing themselves to build the components from scratch, they paid a heavy price in early reliability and operational readiness, but they bought total industrial independence. The knowledge gained from struggling with the J-11B directly fed into the development of the J-15 carrier-borne fighter, which is essentially a structurally reinforced flanker adapted for naval operations. It provided the avionics and weapons integration experience necessary to build the J-16, a highly advanced two-seat multi-role strike fighter that forms the current backbone of the PLA Air Force's offensive capability. Even the Russians, initially furious over the brazen theft of their intellectual property, eventually had to accept the new reality. China had learned everything they needed to know about the flanker platform. When Russia later sold the highly advanced Su-35 to China, it wasn't because China desperately needed the airframes. It was widely understood that Chinese engineers primarily wanted to examine the Su-35's thrust vectoring engines and advanced electronic warfare suites to further iterate on their own domestic designs. The student had comprehensively absorbed the master's technology, reverse-engineered the Empire's jet, and repurposed it to secure their own airspace. The Shenyang J-11B stands as one of the most fascinating transitional aircraft in modern military history. It is a monument to brute force industrial espionage, a testament to the brutal realities of aerospace engineering, and a perfect case study in how political will can force an industry through years of failure until competence is finally achieved. It started as a stolen shell, plagued by heavy radars, failing turbine blades, and compromised flight control laws. It ended up being the Rosetta Stone that unlocked the 21st century for the Chinese Air Force, proving that sometimes the fastest way to learn how to build the future is to completely dismantle the past, piece by agonizing piece. If you like this deep dive, leaving a like helps get it out to other military history fans. Thanks for being here.